start with thanking the organizer for having me here. And I'm really sorry that I was not able to be on site. Actually, I wanted just to arrive on site, but the COVID situation changed my plans. And by the way, that's why today I have to split my presentation into two pieces, 30 minutes and 30 minutes, because an overlap with the class I have to teach. But there is a sort of silver lining to this arrangement. So I will try to give my presentation in the form of detective series. So today I will introduce the crime scene and hopefully mention the main suspects, but the actual crime solving will happen tomorrow. Okay, so when charge quantization leads to the Halon effect. So let us start with charge quantization, because this is the notion which is relevant, the charge quantization or its absence. Both notions are or situations are very relevant to quite a number of talks which we heard at this workshop, Fermi polarance, Bode polarance. So those deal with, one of them deal with quantized charges, well-defined charges, and other ones deal with charges which are not quantized. So let me start with the basic definition, which will play a very important role in what I'm going to tell you. Okay, somehow. Okay. So what do we mean by particle charge of an impurity or excitation? Because in a broader context, we can speak of excitations, not necessarily impurities. Impurities are just some particular special form of excitations. So my definition is very simple. By the particle charge, where by particle I do not mean the impurity, I mean the particles of underlying medium, by the average. This is also important because if this charge is not a good quantum number, we should think of something average. So the average particle charge of an impurity or an excitation is the integral of the number density distortion of the medium around the impurity or excitation. If the impurity is static, then it's just the integral over the density profile of the distorted density, which is typically finite, and everything in place. If the impurity is mobile, we just need to deal with the correlator, and we need to integrate the correlator of density distortion away from particle, which leads to essentially one and the same. And we say that the charge is quantized if the integral is insensitive to variation of systems parameters, like with Fermi polaron or molecule and dimer, trimer. If it's a Fermi polaron, if the medium is an ideal Fermi C, the charge is quantized for a mobile particle, by the way. For the static, it's not. We will be discussing a bit later. For a Boris polaron, if it's a mobile or static impurity in a Boris gas, the charge is not quantized. It's sensitive to all the details of the interaction of the particle with the environment. I will be really interested in the situations when the charge is quantized, apart from the protocol of measuring the charge, which I will be discussing next, because the protocol, I believe it's interesting on its own. So if the particle charge of an impurity or excitation, happens to be a sharp quantum number, in the sense which I will be discussing below, so in a sense of real quantum measurement of the charge, which retrieves an integer number, then the charge is necessarily quantized in the sense of definition 1. However, the opposite is not necessarily true. Think, for example, of quantized fractional charge in quantum Hall effect. If we have a measuring protocol which measures the charge in terms of integer number of electrons, obviously this charge is not a sharp quantum number, but it is quantized. So in my talk, in the rest of my talk, I will be dealing with the situation when the charge, if it's quantized, is also a sharp quantum number. So we do not need to discuss this kind of slight difference. So particle charge of an impurity as an expectation value if it's not a sharp quantum number of a quantum of 0. So let me formulate the protocol of quantum measurement, which retrieves an integer charge no matter what is my state. So it's important that the protocol itself will be always retrieving an integer, be it, say, a Boris polaron where the charge is not quantized, be it a Fermi polaron where the charge is quantized, because as we remember, if we are talking of quantum measurements, the eigenvalues of the measurement are the properties of the measuring device, not the property of the system. The property of the system comes in the form of sharpness of quantum numbers. So some quantum numbers being retrieved stay the same with some states, then we say that the state is characterized by corresponding quantum number. Some of them do fluctuate. So
Boris, again, linguistic question. If you are talking about the phenomenon which is causing the alteration of the background density by the impurity, why do you use the term particle charge of the impurity instead of like kind of background charge or something? Because actually you are talking about what impurity makes with background.
Charge. By particle, I mean the particles of background. Yes, it's a question. By particle, I do not mean the impurity. The impurity can be just a static.
I see.
So can be absolutely no particles in terms of the impurity as opposed to say mobile Fermi polaron. So impurity is not necessarily a particle. It can be just a static.
Yeah. That's clear. Yeah. So particle to make it distinct from impurity.
Absolutely. Thanks for asking. It's an important question. So by particle charge, I mean the charge in terms of the particles of the background, like in Landau Fermi liquid theory, the particle charge is actually the charge in terms of bare electrons. Okay, so the particle is the particle of the background, not the particle which is an impurity. Thanks for asking. It's really important. Okay, so that's the protocol of quantum measurement. I believe this protocol is interesting on its own, and it will be actually interesting to implement it in the experiment, because you will see that the protocol sounds very relevant to quantum microscopy in 2D. So suppose I have a state, say a pure state, pure many-body state with an impurity. And my first part of the protocol is just to localize the coordinates of all the particles by, say, imposing an optical lattice. If my system is in an optical lattice already, I just increase the strength of the lattice so that there is no tunneling anymore. If my system is a continuous space system, like Bose gas or Fermi C, I would have to impose an optical lattice strong enough to suppress, for all practical purposes, all the tunneling. So now my particles are trapped in individual webs. And then I need to process the image. And I will be processing the image, I will explain how, in such a way that as a result of processing, by the very nature of my processing process, irrespectively of the state which I am working with, the original state, obviously I just crushed it by applying this protocol, I will be retrieving some integer, 0, -1, +1, +2, -2. So the outcome will be an integer by construction. So this is a typical measuring protocol. The numbers which are retrieved are defined by protocol, not just by the state. The state just tells me whether there are fluctuations or not. So let me show you a cartoon. So I have some particles which are localized. So they are localized, speaking practically, by a certain optical lattice, but I do not show the lattice, it's irrelevant. So the coordinates are localized. And this gray circle is just my impurity, it's also localized. So the impurity originally could be mobile, could be static, but when I implement the protocol, everything now is localized. And now I introduce a reference geometric object in the form of a lattice. So this object is not physical, it's just how I process my image. I introduce, say, a square lattice, usually geometrically, such that the number of sides, the density of sides, coincides with the average density of my particles. So actually I care only about the sides of this auxiliary lattice. So I show them with red dots and immediately erase the rest. So actually I want to deal with my blue dots, which are my localized particles. And with red dots, the numbers are the same, the spatial arrangements are different, and I want to process my image. So how do I do that? Well, I select the closest pair of particle and lattice side, and I annihilate them. Then I select the next closest, and this is a sort of renormalization. I eliminate, annihilate the closest pairs. Each step, each renormalization step eliminates some pairs. And now if we are patient enough, we continue renormalization. We keep doing renormalization. Of course, we are mostly interested in what happens around my localized impurity. You see now, somehow my impurity stays alone. So I keep doing the renormalization. So the scale, the typical interparticle distance increases because the closest guys are eliminated. And I have to stop at some point when I reach some reasonably large scale. Academically speaking, macroscopic, but speaking practically, the scale which is much larger than typical interparticle distance. And I need to look at my impurity and to see what's going on around it. So this black square, it just gives you an idea. I look at this black square, so square, it's supposed to be large enough, much larger than the original interparticle distance. And let us discuss what is the outcome, because the outcome just tells me what do I measure, what do I define as the particle charge of the impurity. So here are some typical outcomes. The one which I introduced on my previous slide is this one. My impurity stays alone, in which case I say the charge which I observed in this measurement event is zero. There is yet another way of seeing this zero. It's just below. We have a red dot, which is the side of the auxiliary lattice. Nearby, we have a blue dot, which is a particle reasonably far away, but the net charge is still zero, and we understand that if we will keep renormalizing the image which you see here below will ultimately become the image which we have above. So basically, in both cases, it's just the charge zero. We can get the charge 1, like here. That would be our outcome if we do the Fermi molecule dimer. And this one would be just the Fermi polaron with the charge 0 in terms of the underlying particles of the Fermi C. In principle, we can get the charge -1. This situation will also be relevant for my discussion. And as I already mentioned, this charge 1 or this charge -1 can come in a funny way when we have a particle at a distance, and we can say, oh, maybe it's just some rare event. That's possible, exponentially rare event, or some loosely bound particle or loosely bound hole, if the language of particles and hole is relevant for the state which we are studying. So let us discuss a little bit of what we have if we perform a sequence of measurement, because obviously just one measurement tells us little, maybe even nothing, about the state being measured, because as we already mentioned, the integer number, the integer charge, is a property of the measurement protocol. not yet the property of the state. To figure out whether it's the property of the state rather than measurement protocol, we need to repeat the measurement and see whether the number, the integer which we retrieve, is sharp, one and the same for all the measurements, or whether it fluctuates. If it fluctuates, we can just average over all possible outcomes, and that would be precisely the charge in the sense, average charge in the sense of our definition of R. Because alternatively, we can just construct the average density profile, and obviously this expectation value of our quantum observable will just be equal to the integral over the density profile. So the trivial case, or the simple case, I would say that the Fermi polynomial is not quite trivial, is when we see one and the same charge each measurement. The charge 0 in this example, once again, it's just the Fermi polynomial case. We can see the sharply defined charge 0. So anytime we do the measurement, we see the charge 0, but somehow we see that this 0 can come in a non-trivial way. So suppose each time, or almost each time we do the measurement, at some point of renormalization, we retrieve the situation like that. We have the negative charge -1 next, very close at the microscopic distance to our impurity, while the charge +1 is far away at a certain anomalously large distance. In this case, we say, yeah, the charge is a sharp quantum observable. However, the state is interesting. It corresponds to a weakly bound state of a particle and a hole. We can have such a situation in a Mott insulator, for example, under certain conditions. Obviously, the charge can be just a bad quantum number. So the outcome 1 yields 0, the outcome 2 yields -1. Both situations are, roughly speaking, equally probable, like 30 and 70%. Then the charge is a bad quantum number. It's like we are having a bump, a repulsive potential in a Bose gas. That would be our typical outcome if we just have a bump, a static bump in the Bose gas. It just repels particles sometimes. So if the bump is not particularly strong, the outcome 1 will be quite probable. The outcome 2 also. So kind of, because say the charge on average is -1/2. So we do repel particles, but we cannot even repel on average 1 particle. So that would be our typical outcome for this situation. The charge is not sharp quantum number. It's not quantized. It's sensitive to all the details of our bump. We make the bump a little bit stronger, the probabilities change. Now, let me define what do I mean by the Halon effect. I will not be at this point, I will just define the effect, but I will not explain when are we supposed to see it. So if you will, I'm introducing you to the crime scene, and only then I will be able to kind of introduce you to the main suspect and then solve the crime, show that such a situation is really possible, because the situation, as I define it, sounds to be really exotic. So I want my charge to be a sharp quantum number. It's sharp, it's one and the same, always. However, I want my outcomes to come in 2 distinctively different forms. So one way how I can observe the charge 0 is just I see the bare impurity after a number of steps. That's outcome 1, say, happening with, say, probability order 1, say 50%, 30%, or something like that. But there is outcome 2, where the net charge is also 0. However, in this outcome 2, I always see the situation with sort of asymmetric with respect to the particle and whole with respect to the positive and negative charge. say negative charge stays always close to my impurity at a microscopic distance, while my particle, positive particle charge, is typically far away. So you see, it's something exotic. If I am dealing with a pure quantum state, of course, if the state is not pure, we can say, oh, it's a 50-50 mixture. But if my state is a pure quantum state, I understand that I'm supposed to deal with some quantum entanglement, where within one and the same non-degenerate ground state, I'm talking about the ground states, I can produce two very different outcomes in terms of the distribution of the charge. If I will translate it into the density profile, it will be a very strange density profile featuring a halo, a large halo away from my impurity. The presence of this halo gives the name Halon to the effect. The Halon effect is all about the halo. So, large distribution of the density, and actually the integral under this distribution is not integer, it's fractional. My example will be exactly 1/2, by the way. The halo is large enough. Okay, so before we will embark on the discussion of how we can produce this Halon state, we will see that it's very non-trivial. Let me mention a more simple problem, which we actually discussed a little bit on the day one after the talk on Fermi polarance, when there was a question of the criticality of the transition between different charge sectors. So if we have different charge sectors with sharp quantum numbers, the next question to discuss is there some non-trivial criticality when we essentially do something with our Hamilton parameters of our Hamiltonian, the ground state changes, the ground state of the impurity changes the sharply defined charge. Is there anything non-trivial? There are many cases when the transition is trivial. So if the system has gap like Mott insulator, the charge of an impurity is a sharp quantum number, but the transition is absolutely trivial. We have just two different states which are not talking to each other, like apples and oranges. And there is a point, formal point, when the two energies are equal to each other. It's sort of first order phase transition, very boring, nothing to discuss. There is almost equally boring situation which takes place with Fermi polarance, when actually we have so-called asymptotic metastability, but you will see that it's pretty much the same as this coexistence, because we have two states, a metastable one with larger energy, say the polaron and a molecule, dimer and trimer. So the state which has larger energy is unstable. It can decay into the state with lower energy and fermionic excitations. However, on the approach to the critical point, the lifetime becomes progressively larger in such a way that the decay width shrinks faster than the distance between two branches, meaning that asymptotically, two states become well defined, and right at the point, we have just the degeneracy. So we have just two different states. So the situation like that. First order, if you will, type of the transition. And what I'm interested in, what the Halon effect will be all about, is this non-trivial situation when we have two branches with two very well-defined charges. But there is absolutely no way we would have anything metastable beyond the critical point. So at this point, we would like to have some non-trivial full-scale criticality with scale invariance and stuff. So let me stop at this point. So the main suspects will be introduced later. So the detective series is supposed to actually solve the crime at the very end. So in the second part, I will introduce the main suspect and hopefully solve the crime. Thank you very much for today's part of my talk. And please ask questions concerning this part, because I do have some time before I rush to my lecture, or I can just leave the questions to the end of my presentation tomorrow.
Okay, thank you, Boris. We have, as you heard, very limited time for questions, but if somebody have an urgent one. Vadim has an urgent question.
Okay.
I don't know how urgent it is, but I didn't get your cutoff procedure. So you eliminate pairs until what exactly?
Okay,
Until what?
so until the interparticle distance of the processed image becomes much larger, academically speaking, by any large factor, say 1 million, the typical interparticle distance.
Right. Okay.
And when it's very large, I saturate to a certain stable situation. Either I'm left with, so you see, let me just show this slide. So the size of this box is supposed to be much larger, dramatically larger, not by a factor of 2, 3, or 5, but academically speaking, by a factor of 1,000,000 or 1,000 than the typical interparticle distance.
Right.
So, and this size, say, this distance between the blue dot and this gray dot is also supposed to be huge if I'm talking of something semi-qualitative.
Yeah, this is exactly what is a bit confusing. So the size of this box, as far as I understand, is the same as the this infrared cutoff distance. Are they the same sizes?
Cutoff, I'm sorry, what's the infrared cutoff?
Oh, I mean the large distance. So you have the large distance cutoff where you stop your RG procedure.
Right, but this large distance is much larger.
It is much greater than the size of the box.
It's smaller than the size of the box, obviously. So it's much smaller than the size of the box, but it's much larger than any meaningful correlation length. Whatever correlation length.
Okay. Yeah. Okay. So
is larger.
So you eliminate pairs until the distance between the two particles gets much greater than any correlation length in your system, exponentially.
With one exception, if there is some anomalously large correlation length, which actually will be the critical region, this correlation length is left. But
I appreciate that.
Should be much smaller than the size of the box.
Right.
So the idea is to reveal some anomalously large correlation length, if any. That will be the Halon effect.
Okay, but the box is still greater than your cutoff scale. Is that correct?
What's the cutoff scale?
Yeah, the box is bigger than your cutoff. Well, the scale where you stop the RG procedure.
Oh, you mean I see. Not the box which you see on the slide, but the box with the system. The system. Right. So okay. I see the point of the confusion. So this black square is the box where the system is contained. This is where I stopped. This is the scale at which I stopped my renormalization.
The
box with the particles is much larger.
It's much larger. Okay. Yeah.
Orders of magnitude larger.
Yeah, that makes sense.
But the system is irrelevant, academically speaking, of course. Experimentally, there will be a tough situation. We understand how tough it is just to have a hierarchy of scales. Everything will be there experimentally, but academically speaking, yes. So the size of my box, which you see here, is much smaller than the box containing the particles, but much larger than typical correlation length.
Right. Okay, that makes sense. Okay, thank you.
Okay, very good. Thank you.
Okay, any other question?
Yeah, so the box on the slide, it should still be larger than the renormalization scale, because otherwise you cannot be left with the situation where you have a blue and red dot inside, right?
Right. So this is the tricky situation. So at some point, so it's a tricky situation with the hierarchy of scales. So I kind of do renormalization and say keep seeing something unusual. So like I see this one, then I go to larger scale, see the bottom, and of course, if my so so here in the bottom you see that two sizes are more or less equal to each other, the size on the same order, the size of this black box and the distance between blue and gray. But you are right that if I increase my box, say by a factor of 2, I will have, by the definition of my renormalization procedure, I will have to erase red and blue.
Okay, other questions? Okay, if not, I stop recording. We let Boris go for teaching.
Okay, thank you very much. See you tomorrow.
Yeah, and we